A second order system is going to have a second derivative in it. So in this case, we have a generic equation describing our second order system or sensor, which will most often be the case for us, but it can be any system. In this case, I have three coefficients, A2, A1, A0, and those are going with the various derivatives. So I have A2 second derivative of y, A1 first derivative of y, A0y, and that equals f of t. And remember, f of t is my input, my forcing function, effectively. Right, and I can divide both sides of this, similar to what we did for first order sensors, by a naught. And if I do that, then I'm going to get a new coefficient in front of the second derivative term. In this one, I'm going to define based on the natural frequency of my system. So that coefficient will be 1 over omega n squared. And the second coefficient right here is going to be based on both the damping ratio and the natural frequency. In this case, this is going to be 2 zeta, where zeta is my damping ratio, divided by omega n. And then finally, I also have this coefficient in front of my input term, and that's still going to be my K, or my static sensitivity. All right, and let me define these terms as well. So omega n is my natural frequency, and that's in radians per second, and zeta is my damping ratio, and that has no units. That is a dimensionless number. Okay, so I can rewrite this equation based on these parameters that I've provided now. So my kind of canonical second order system is going to be defined as 1 over omega n squared times that second derivative, plus 2 zeta over omega n times the first derivative, plus y is equal to k f of t. Right, so not surprisingly, for our first order system, we had one parameter, basically our time constant tau. For our second order system, we have two parameters that are describing the system, both the natural frequency, omega n, and zeta, which is our damping ratio. Right, as a quick example of that, I just wanted to go through the very basic second order system that you're all probably familiar with, where I have a mass, a spring, and a damper. And another way to think of the order of a system, or the number of energy storage elements in that system. In this case, I can store energy in both my spring with potential energy and my mass with kinetic energy. So I can write down the differential equation here. I'd have my double dot plus cy dot plus ky is my force f of t. Right, I can divide this through by k on both sides, this little k, not to be confused with big K, which is our static sensitivity. And I will get this equation right here. And I just want to go through these terms to make sure they make sense to you. So this m over k, I could rewrite this as 1 over the square root of k over m, that whole thing squared. Right? And as you probably know, for a system like this, the natural frequency of that system is going to be the square root of k over m. Right? So this is equivalent to my 1 over omega n squared that I defined over here. So that's just telling me that omega n for this system is square root of k over m. I can do the same thing to kind of back out what zeta is in terms of c and k, but I wanted to focus on this last term, the static sensitivity here. Right, and I wanted to focus on it to give you a better indication of what that static sensitivity is doing. All right, so K here, my little k, this spring constant is in units of Newton per meter. Right, and in this case, my forcing function, my input to the system is a force. It has units newtons. My output is y, which is a displacement. And so in this case, what the static sensitivity is doing is converting my input units to my output units, right? So by providing 1 over k, and I'm going to put this in brackets to indicate that I'm looking at units here, I'm looking at 1 over Newton per meter. So I'm going to get out meters per Newton, right? So my static sensitivity, K, will have units of meters per Newton. And that is because that static sensitivity is translating the input units to the output units, or the input to the output. So now that we have a good description of our second order system, we need to come up with the solution to that second order system. So we have an understanding of what the output will look like over time. I'm going to rewrite that equation describing our second order system, so we have it here for us to look at. Okay, and similar to the first order systems, I'm going to look at two different inputs as possibilities going into this second order system. So I'm going to look at a step input, and that step input I'm going to define as 0 until time equals 0, amplitude A after that. And then I also might have a sinusoidal input, and that is also amplitude A. All right, so we're going to start with this step input. And honestly, for the step input, one of the really, all of these are going to have some interesting solutions to them, and fairly complex solutions. But for the step input, we do know some basic information about kind of the steady state response, at least of our system. So y of t in general is going to be the sum of the y in steady state plus some transient, right? And remember, in our first order system, that transient was just the decaying exponential, effectively. All right, and so our steady state is going to be similar to what we had in our first order system. Over time, it's going to die out, and I'm going to have this static response to my input. So if I just look at that steady state response, right, I have effectively my static sensitivity times the amplitude of my input, right? So which is Ka, which means that if I look at y of t over time, I at least know this one thing, that I'm going to end up at Ka here, and maybe I start at y naught, right? I don't know what's going on between here and here yet, but I do know that at long time t, I'm at Ka for my response, and at the very beginning, I'm at y naught. So for the transient part of this response, I'm going to want to look at the roots of this characteristic equation. So I could rewrite this as a characteristic equation like this. And the roots of that characteristic equation are going to be based on that damping ratio and natural frequency, where lambda, so I have two roots to this characteristic equation, which makes sense, it's a second order system. And these will be minus zeta omega n plus or minus omega n times the square root of zeta squared minus 1. All right, so rewriting that those roots of the characteristic equation, I'm going to have three different cases. All right, case 1. In this case, I'm going to assume that zeta is greater than 1, which means that this amount, this quantity under the radical is going to be positive, right? Which means I'll have real numbers here. So zeta greater than 1, I will have two real and distinct, there'll be different numbers, roots to my equation. This means that that transient response, y of t, is going to look like some constant e to the minus lambda 1t, where lambda 1 is the first of those characteristic roots, plus some other constant e to the minus lambda 2t. Right, so this transient, once again, as we expect, goes away over time. As t goes to infinity, these terms both go to 0. But in this case, right, the rate at which they go to 0 is going to be determined by those characteristic roots, by both the damping ratio and that natural frequency. Right, and we call this case overdamped. So when zeta is greater than 1, when my damping ratio is greater than 1, I'm overdamped. Right, in the second case, I have zeta equal to 1. And in this case, I have two real roots, but in this case, they're repeated. They're the same number up here. Because in this case, when zeta is 1, this term goes to 0, so I have two roots, both at negative zeta omega n. So in this case, I'll have something similar. In this case, both of the roots are, let's say, lambda. So I'll have some constant e to the minus lambda t, but then I'll have another constant times t e to the minus lambda t. So it's a little different from that first equation. And in this case, we call the system critically damped. All right, in my third case, I'm going to have a zeta less than 1. Right? And when zeta is less than 1, this term under the radical is negative, which means that I'm going to have imaginary roots. So here I have two complex, distinct roots. Right? And my transient part of my y of t, of course, is much more complex here as well. Right? In this case, I effectively have a damped sinusoid. Right? So I have some constant. My decay rate is based on that damping ratio and natural frequency, right? And that is multiplying a sinusoid, right, with a frequency at omega n square root of 1 minus zeta squared, which we actually call the damped frequency. So this is omega d is another name that we give for that, right? And in this case, we consider the system to be underdamped, right? We have a very small damping ratio, underdamped, damping ratio of 1, critically damped, and damping ratio greater than 1, overdamped. Let's start with the overdamped system, and I'll provide the y of t, but it's really just a giant nasty equation. All right, so here's the big nasty equation for y of t for the overdamped system. All right, but the important points right here, this Ka term, is what we're going to get at steady state. So that basically is telling me that way out here at large time, my response looks like Ka. Right? I also can look at this giant term right here. I have these exponentials at t equals 0. This will go to 1. This will go to 1. These coefficients subtract such that I also get 1 here. So I just have Ka plus y naught minus Ka. So I am going to start at y naught. So y naught right here is my starting point, which is not surprising because that's based on my definition of the initial conditions. So right here, this big messy pit is my transient response. So that's my y trans of t that we were talking about earlier. I have some constant times this decaying exponential plus another constant times this decaying exponential. Those are the two roots of that characteristic equation that we looked at earlier as well in the exponential. Right, so it's fairly complex, but the key point that I want to make here is that my response is going to look something like this. Right, so I'm kind of slowly going up to that steady state value. And over time, or as I increase my damping ratio, that'll get even slower, right? So I might go way over here, right? And, way over here like this. And that's as my damping ratio is increasing. So this is my overdamped response. I'll have this anytime the damping ratio is greater than 1, right? But my response gets even slower, right? Because these roots are changing right here as that damping ratio is increasing. For my critically damped system, my y of t is a little simpler, right? But I still have my Ka, that's my steady state term, right? I'm always going to have that for this step response is one of the key things that I want you to remember. I'm still going to start at y naught. And what this transient is going to do, and this is due to the two repeated real roots here, is I'm going to rise up like this, and I'm going to rise very quickly relative to the overdamped response, and then hit that steady state and stay there. I don't go above Ka in this case, right? But I rise pretty quickly and I stay at Ka. Right? And that rise is being determined by this transient part of my equation. Right, so that t is changing things a little bit from what I saw in the overdamped response. All right, and finally the most fun, the underdamped system. I'm going to have that same steady state response Ka. Okay, once again, I'm going to be at Ka over a long period of time. I'm going to start at y naught. And these are things that this equation is telling me. Right? There's Ka, that's my static sensitivity and my amplitude of my step. That's giving me my response at long periods of time here, or after a long period of time. And this whole thing right here, similar to what we've seen before, is my transient. Right? But it looks a little bit different from what we had before, right? We have an exponential now multiplying a cosine. That cosine for its frequency has that damped frequency, right? So that cosine is at the damped frequency. That damped frequency is based on the natural frequency of my system and the damping ratio. And there's some phase to that cosine as well. But that's multiplied by this decaying exponential, which means that I have this kind of decaying envelope on this sinusoid over time. So what that means is I'll have this kind of exponential envelope here, but my actual response looks something more like this, right? So that those exponentials are providing an envelope on this sinusoid. So this sinusoid is operating at the damped frequency. So this period right here, I'm going to call TD, is related to the damped frequency. It's not the natural frequency, so it's a slightly modified version of that natural frequency. Okay, and this envelope is e to the minus zeta omega nt, right? That's my exponential that I have right there. Right, and that leads to some metrics that are of interest for our underdamped systems. So I can look at this period here, right? And this is going to be TD. It's going to be my damped period. And that's going to be related to my damped frequency, omega d. So if I had a response from a second order sensor, I could actually figure out what the damped frequency of that is based on measuring this period right here. Right? I'm also going to define a settling time, basically the point at which I end up within 10% of my final value here. So this is Ka plus 10% of the total step. In this case, the step was 1. I went from 1, which was my y naught, to 2. So 2.1 here, and this is Ka minus that 10%. Right? And that, once I'm kind of within that boundary, and it looks like I am within that boundary around here, right? That is my settling time right there. So TS is my settling time. And this is a settling time based on a 10% metric. Sometimes you'll see a 2% settling time instead. I also define the rise time as the point at which I'm at 90% of my total step height, which would also be here in this case. So this time right here would be my rise time. So TR is my rise time. Right? And I can also get some sense of the number of peaks will give me some sense of that exponential envelope, and that would give me my damping ratio as well. So the key point I want to make here is that from a basic response plot, step response plot of a second order system here, you can figure out what those parameters omega n and the damping ratio are, much like we could figure out the single parameter for a first order system, which was tau.